Welcome to the very first video we have for our new unit today, guys. We are introducing integration today, and actually we won't actually get to integration. What we're going to do is we're going to introduce a concept called approximating area. Eventually this will lead us into integration in the next couple of videos, but not quite yet. So when it comes to area, I mean, we don't always have to approximate area. Sometimes when we have specific shapes, we can find the exact area. So we have a lot of, let's see here, if we have formulas for finding the area of a triangle, 1/2 base times height. We have formulas for finding the area of a circle, pi r squared. We've got the area for finding a rectangle, and we even have for if it's a regular, it's hard to draw a regular one here, but if it's a regular pentagon, 1/2 apothem times perimeter. Same thing for if we have a hexagon here. All these different shapes. We have eventually figured out how to find the area using our geometric principles to find the area of all of these different crazy shapes. So what comes into play though is how do we find the area of this shape? Ooh. What's happening here? So just like finding the areas of all these other shapes, we kind of had to do some trial and error here. So, the first approach, Archimedes called it the exhaustion method. So in order for us to come up with the method of finding the area of a circle, for example, what they did was they would find a polynomial, or not a polynomial, a polygon that could fit both on the outside and one on the inside, find the area of both, subtract the two to find the difference, and then eventually make that polygon have more and more sides to where it eventually exhausts it to the point where it's like almost a circle. Okay, so they were approximating circles, and that's eventually how we found the relationship of pi. Okay, well that's cool, but how does that relate to this guy right here? Because this isn't a circle, this isn't a square. So what they did was they were like, okay, well how do we get as close as possible here? So what some people could do, and what I would suggest is to kind of give it your best guess here. See, how would you find the area? Like what would you use to approximate? So you could draw this big rectangle right here, and then I could say, well, some of this is below the curve, some of this is above. Like I want this area but not that, but so maybe I'll just take the I'll just do this right here, and this rectangle would be a pretty close approximation of this whole area. It's not going to be close, but again, we're approximating, right? There's nothing wrong with that. So that's one method to this one. What other people said that they could do was, okay, I want to make it a little bit more accurate to that. So we're going to go ahead and keep the big rectangle like we had before, but then let's break this up into smaller. So we have a full rectangle here, but then I'd have to make smaller. Okay, I could do a triangle here. I could do another rectangle here. I could do a triangle here. I could do another triangle here, and then I could make this like a weird trapezoid thing. If I wanted to, I could go here's a trapezoid. It's kind of a little too much there, but then I kind of account for that. Just lots of different things, lots of different shapes. Okay, so that's another way to do it. Give this a try on your own. Go ahead and try some things out, add the blocks together, see what you get, come back and see what we did. So hopefully you've tried some things, but all these things that they kept trying over and over again, just like you guys are trying to do, the only downside is there's not like a set pattern to do the same thing repeatedly. So what they needed to come up with was okay, so we know we're going to have an approximation here, but we need to have some form of clear, distinct pattern that we're going to do, because that's what math is all about. We try to accomplish something, we create a pattern, and then we try to come up with the math behind said pattern. Okay, so as much as they like to do all of these different these different scenarios here, what they started to do was, okay, what's the biggest shape I could come up with that would encompass this whole thing? Okay, again, I don't want to make an exact area. I just want to approximate it. So the biggest one they could have would just be a simple rectangle. If I wanted to, I could go all the way up, but I don't have to. I can do this right here. I could do this rectangle right here. And that's a pretty good approximation, okay? Well, but then I need to have a specific place for the height for this rectangle. I know the width of the rectangle because I know exactly how far my function goes. Okay, so then what we're going to do here is we're going to say, okay, we're going to take the highest point, which happens to be in this case on the farthest right hand side, okay? And it doesn't have to necessarily be the highest point. We just need to have a methodology here. So how about we just say, all right, let's always go, let's make a rectangle. Okay, let's make a rectangle, but let's always use the height of our rectangle as whatever the function value is on the right-hand side. Okay, so that means you would have this y value, whatever it is, that's going to be the height of your rectangle, and then the width of the rectangle is whatever that x value is down here. Okay, again, now this is going to be an approximation here, right? So it's going to be pretty close, but it's not going to be 100% accurate. So then they're like, all right, well, I like using the right-hand side. That's fine. But it's too big. It's got all of this extra area right here. So how could we make that a little bit closer? Okay, well, what if we still use rectangles, but we did two rectangles? And instead of using just the far right-hand side of this rectangle, let's break it into two rectangles of equal width here. So how far does this go? 1, 2, 3, 4, 5, 6, 7, 8. So let's go to 1, 2, 3, 4. And then since I use the right hand side for the height over here, I'm going to use the right hand side of this square. So 1, 2, 3, 4. And I'll make this rectangle here. And I've got my other rectangle over here. Okay, so this one is going to be kind of an over approximation, but this side over here, it's kind of hard to know for sure if it's an over or an under approximation. So it's pretty close, but I feel like it's still closer. It's closer than what we had before with this one big rectangle. Okay, well then how could we make it even more accurate? Well, we could increase the number of rectangles. So instead of 2 rectangles, what if we did 4 rectangles? So I've got the right hand side of this rectangle, the right hand side of this rectangle, but let's break this up. Instead of 1, 2, let's go 1, 2, 3, 4 rectangles. Now notice this rectangle right here, okay? All right, the height of my rectangle depends on the y value on the right-hand side. Okay, so this rectangle here, again, the height depends on the y value on the right-hand side. Over here, same thing. Over here, same thing. So again, this is going to be, like this rectangle over here is going to be a pretty big over approximation, but I've got a couple of under approximations over here that might help balance that out. And this is another over approximation, but that's okay. It's still more accurate than what we had by just having a big rectangle over the entire thing. Okay? So this is what we call the right-hand approximation method. Okay? So we're actually going to use that same method, but we're going to use it on a different function, 5 minus x squared. So I'd go ahead and draw this function on your paper. If you need some grid paper, I have plenty of it at the front of the room, or if you just have graph paper at your desk, that's totally fine. Go ahead and sketch this function. And what we're doing here is I want to approximate the area of 5 minus x squared from the points 0 to 2, and this n right here is the number of rectangles that I want. Okay, that's how many rectangles I want. I want it to 5 rectangles. Again, if I wanted to, I could make it more accurate by adding or by increasing the number of rectangles. But after a while, it gets kind of cumbersome. So let's just do these 5 right here. So to do that, let's go ahead and look at where these rectangles go. So I'm going from 0 to 2. And I intentionally drew this on my grid paper to where I had, you know, it takes 5 squares to get to 2. So you might want to check that on your own. That's fine. Okay. But I know I'm going to draw 5 rectangles from 0 to 2. So that means I know what the width of each rectangle is going to be. What is the width of each rectangle? How do we figure that out? I know that I'm going from 0 to 2, and I'm trying to find I know that I have 5 rectangles, so the width of each one is going to be the distance divided by the number of rectangles. So the width is going to be 2 divided by 5, so just 2 fifths. In general, how did I come up with that? Well, if I'm going from 0 to 2, I took my second value minus my first value to find that distance. So we're going to call that b minus a, where this is a, this is b. You're on the interval from a to b, divided by n. Okay, n being the number of rectangles. So the width for this specific one is 2 fifths, but in general, it's always going to be b minus a over n. Okay, another thing we could call that is delta x. Ooh, or the change in x. And let me show you why we call it that, okay? So if I'm starting at 0, and I know the width of each rectangle is 2 fifths, the change in my x values from this x value here to this one is 2 fifths. It's going to be that delta x, okay? So from here to here is 2 fifths. So that means this next point is going to be at 4 fifths, 6 over 5, 8 over 5, and then I'd be at 10 over 5, which is the same thing as 2. So these are the x values I'm going to use to help me find the y values on my function. Okay, and I determined those by looking at my delta x, or the width of each rectangle and where I started from. Okay, so what I'm going to do now is let's go ahead and draw these rectangles here. So I am using for each, so I'm going to draw a rectangle between these 2 points. The height of my rectangle depends on the y value of the right side. Okay, so I have 0 and I have 2 fifths. The rightmost coordinate between these two is 2 fifths. So the height of my rectangle is going to go to the y value, or f of 2 fifths. Okay, so I'm going to draw this back here. There you go. I've got my rectangle. Okay, the base is 2 fifths. We know that. The height is going to be f of 2 fifths. Well, I don't know what the f of 2 fifths is. Oh, but I have a function. I can go ahead and plug that in. So 5 minus 2 fifths squared. Well, 2 fifths squared would be, let's see, 4 over 25. 5 minus 4 over 25 is going to be 121 over 25. Okay, that is the y coordinate. That is the height of this rectangle right here. Okay, so then I'm going to repeat that process at 4 fifths. So I'm going to go to the y value at 4 fifths. Okay, I need to figure out what that is. F of 4 fifths. 4 fifths squared, so 16 over 25. Take that away from 5. That's going to be 109 over 25. Okay, repeat that over here. So then f of 6 over 5. So 36 25ths from 125 25ths. So that's going to give you 89 over 25. This guy right here is f of 8 over 5. And that height is going to be 61 over 25. And this last rectangle here should be pretty straightforward. 2 squared is 4. Take that away from 5 and you get 1. Okay, so the area of each rectangle is what we are using to approximate the area of the entire curve. Okay, I found the height of each rectangle based upon the y value at the right hand coordinates. Okay, the width of all of them are 2/5. That way it's a nice uniform number all the way through. Okay, so my area is always length times width. Okay, but I have to do that 5 times. So the area is length times width. Let me scroll down here. So then my first rectangle is going to be 2/5 times that, oh, I went too far, times 121/25, plus this rectangle is 2/5 times the height, which is 109/25, 2/5 times 89/25, 2/5 times 61/25, and then 2/5 times 1. Okay? If I wanted to, I could shorten all of this to say 2/5 times 121/25, 109/25, 89/25, 61/25, and 2, nope, I already had the 2/5, plus 1. Okay, the reason I write this like this is I'm trying to see if there's a pattern here. Okay, if I wanted to, I could go ahead and type all this into my calculator, and this gives me 6.48. Now notice I use my approximation symbol because I don't know exactly what the area is. I know that it's approximately 6.48. We're not at the point yet where we can find the area exactly. Okay. So again, I wrote this like this so we could find a pattern here. So 2/5, well, that was the same thing as the delta x we had earlier, okay? And this was the function value at 2/5, 4/5, 6/5, 8/5, and 2. So let's scroll down again here. So I'm going to think of this as 2/5 times f of 2/5, f of 4/5, okay, so that's how I came up with the area. Well, I need to get a more generalized rule than that. So what I'm going to do here is I'm going to label each of these terms here as I equals 1, I equals 2, okay, because this was the first iteration, second, third, fourth, fifth. And you're like, iteration, she's throwing out some weird words here. Just hang on a second. I have a goal here. I have a goal in mind. It's on its way. Okay? So basically what I have here, we already determined that this was delta x. So this is f of my first x value, right? So x1, f of x2, f of x3, f of x4, f of x5. Does anyone remember what it's called when we add a certain number of terms together that follow a specific pattern? Anyone? Anyone? This is what we would call a summation. So what we've done here is, in general, we have found the sum from I equals 1 to 5, in this case, okay, of the function of x squared. No, what was it? 5 minus x squared. My bad. 5 minus x squared. Whoa. xy, I should say. Actually, I wrote in general. Hang on. I got this, guys. Bear with me here. This is how I teach it on a normal basis. You guys have experienced that. I write things down and I'm like, wait, go back. Okay, so for this one right here, okay, I've got I equals 1 to 5. My function was 5 minus x sub I squared, there we go, times 2/5. Okay, this is specifically for this situation. In general, Okay? I always start with I equals 1. Okay? This 5 was the number of rectangles that I wanted, which was n. We wrote that down earlier. This is my function. Okay? So f of x sub I. Okay? And I write x sub I because it's like I want to evaluate at the first x value, the second x value, all the way up to however many x values that I want. But then I have to multiply all of them by the width of my rectangles, which was delta x. This is the general formula for a right-hand approximation. Okay? This is our general formula for a right-hand approximation. Basically, I'm creating rectangles at a specific width that has already been specified to me because I already know the number of rectangles that I need, but I also need to evaluate the height by finding the y values at the right-hand side of my intervals. Yeah? No? Maybe? Okay. Well, let's try. Let's say we didn't want to do the right-hand side. What if we wanted to do the left-hand side? How does that change things? Okay, so if you need to, you can draw this again, or you can write it on the same function. Either way is fine. So here's what we got. Start at 0, still have 2/5, 4/5, 6 over 5, 8 over 5, and 2. Okay, but now if I want to do a left-hand approximation, oh, this was still I equals 1. That hasn't changed. 1, 2, 3, 4, 5. Okay? But now, my rectangle, instead of going up to the height of my rightmost term, I'm going to get the height from my left term. So between these two, the height of my rectangle is going to come from this guy right here. So I'm going to go up to f of 0 and then draw my rectangle. So f of 0 now determines my height, which in this case is just 5. Okay, now this was I equals 1. Ooh, so if that's I equals 1, 2, 3, 4, I need to go back 1. So I'm going to label this guy as I equals 0. Okay, I can just go back one step, and that's totally fine. It's legal, I promise, guys. Between 2/5 and 4/5, the height of my approximation, the height of my rectangle here, is going to come from the left side. So the y value at 2/5, there we go. Then I draw my rectangle. So then this is f of 2/5, which you know from before was, how much was that? I already forgot. 121 over 25. Okay. Same thing between 4/5 and 6/5. Go to the 4/5 height. Go over. Boom. There we go. So the height of this one is now f of 4 over 5, which we said, I believe, was 109 over 25. So between 6/5 and 8/5, the height's going to be on the 6/5. So f of 6 over 5, which was 89 over 25. And then f of 8/5 right here. Between these two, that's going to be the height. So then f of 8 over 5, which again we already know was 61 over 25. Okay, so look at the two rectangles, or look at the two drawings here. Let me go back a page. This was my right-hand approximation. Do you see how all of the rectangles were below the curve? They all ended up being below the curve. This would provide an under approximation. But now, if I did a left-hand approximation, all of my rectangles are above the curve. So this would be an over approximation. I'm fully aware that it's not completely accurate, and then it's okay. The whole idea is to make this an approximation. Okay? So now, to find the area, I would add these up again, just like I did before. So I would say area is still length times width. I already know that each one of these is going to be a width of 2/5, so I'm going to skip a step here and make this 2/5 times 5 plus 121 over 25, 109 over 25, 89 over 25, 61 over 25. Okay, did I get all those? 1, 2, 3, 4? Yes, I got them all. Okay. Notice I didn't do anything with the y value at 2. Okay, I don't need it this time because the height of my rectangle now comes from the left side, not from the right side. Okay, well again, this guy right here was delta x, right? This was f of x naught. I'm sorry, when I say x naught, here, 2/5 times f of x 0, x sub 0. I don't know if I've said that in class or not yet up to this point. I call x sub 0 x naught. That's just an old habit from college. Oops, that should be a 1, not an I. 1, f of x 2, f of x 3, f of x 4. Okay, and then this guy was still my delta x here, right? So I could leave about 2/5 or delta x. But in general, this was the summation, or specifically for this one, from I, if I started it at 1, because I like to start this at 1, 1 to, I still want 5 rectangles. So I like to start this at a 1 and imply that I'm going to 5 rectangles, okay? My function is still 5 minus x of something squared. I don't want to just say I, though, this time. Because if I put an I right here, that means I'm going to start at I equals 1. But that would start me here. I need this guy right here. So if I do a minus 1 right here, that kicks me back to where I start at x equals 0, and x equals 1, 2, 3, and then up to 4. And then I multiply by 2/5, which is my delta x. So this was specifically this function. But in general, this would be I equals 1 to n, the number of boxes, however many you want, okay? And it's going to look very similar to the right-hand one. You had f of x, but you're going to have I minus 1 right here, delta x. This is called the left-hand approximation. Okay, the two formulas are very, very close to each other. It's just that I have an I minus 1. Oh, I minus 1 squared right here. Or I minus 1, the function itself is squared, but just an I minus 1 right here. Okay. Oh, I forgot to actually tell you that the area, if you plugged all that into your calculator, maybe you did, maybe you didn't. Oh, I forgot. Approximation. 8.08. A little bigger than what we had before. Okay. But we knew that it was going to be an over approximation. So we had the left hand, we started out with the right hand side. Then we did the left hand side. Okay? I hope this makes sense. If you need to come back and watch it again, that's fine. As always, you can always go to Prof. Rob Bob and all those next ones. But what if I wanted to make this even more accurate? Because some guys are like, well, the left hand side is too high. The right hand side is too low. What if we found the value right at the middle, right in the middle of the other two? Well, that's going to be called, the midpoint approximation. Okay, again, same function, 0 to 2, same number of rectangles, and I had from 0 to 2, 2/5, 4/5, 6 over 5. 8 over 5. But now I don't want to evaluate it at these points right here. I actually want to evaluate my function at the midpoint of these two places. Okay, so then my rectangle, the width of it is still going to be 2/5 all the way across. Okay, but now the height of my rectangle is going to depend on the y value of this x coordinate. So if I'm at 0 and I have 2/5, in between is going to be 1/5. So f of 1/5, about right here, will give me the new height of my rectangle that I want. And I feel a little bit more confident about that because if I notice here, I've got a little bit underneath and a little bit over. So maybe we're going to be a little bit more accurate. Okay, so f of 1/5, if I plug that in here, that's going to give me 124/25. So that is the height of this first rectangle that I have drawn here. Okay, my next rectangle, the height is going to come from f of 3/5. So I go up to here. So this is f of 3/5. Which I will tell you is 116/25. Okay? Between 4/5 and 6/5 is just 1 because it's the halfway point here. So f of 1. Boop. Oh, and that lovely works out to a nice pretty number of just 4. Okay? In between 6 and 8/5 is 7/5. So this height comes from f of 7/5. Boom, right there. There we go. Okay, and then my last one, 9/5 is in between, so that height is about right there. F of 9/5. Oh, I forgot to write this one. F of 7/5 is 76/25, and this one is 44/25. Okay, so to find my area, I'm going to add all these rectangles together. So area is still length times width. So 2/5, because I know even though I'm evaluating that at a different spot than I did before, the width of every rectangle is still 2/5. Okay, so now I've got, let's see, 2/5, 2/5, 124/25, plus I'm going to have 116/25, 4, 76/25, and 44/25. Did I get them all? 1, 2, 3, 4, 5. Yeah, we're good here. Okay, if I were to add all that up, this is approximately 7.36. Oh, that's kind of in between the two numbers that I had before. So like we've done in the past, so I need to come up with like a mathematical pattern here. This was still I equals 1. Those numbers haven't changed. I like to keep those exactly where they were. I equals 0. So that way we don't get confused. Because if I change them all around every time, it's gonna get messy, okay? So this was 2/5 times. Now instead of f of these two numbers, this was actually the midpoint. So this was the midpoint of I equals 0 and I equals 1, right? So this was x sub 0 plus x1 over 2. I'm using my midpoint formula, because if I add those two together and divide by 2, that gives me the midpoint. And this was x1 plus x2 over 2. This was f of x2 and x3 over 2, x3, x4 over 2, and then f of x4 over 2. All of that was multiplied by 2/5. Whew, that looks intense, but it's really, really, honestly and truly not that bad. Because what we're going to do to generalize this whole thing is, I'm going to give you the general formula this time, and then I'll come back to the specific one. So in general, we're going to have I equals 1 to n, the number of boxes. It's the midpoint approximation. So f of, let me make that f a little bit bigger, x of 1, or x of I, plus x of I minus 1, the two previous terms together, all over 2 times delta x. And specifically for this one, we had I equals 1 to 5. We did 5 minus x of I plus x of I minus 1 over 2 squared times delta, oh, no, sorry, times one more, 2/5. Okay, this is called the midpoint approximation. Okay, because instead of evaluating at the left-hand side or the right-hand side, I'm evaluating my function at the midpoint between my x coordinates, and that's going to give me the height of my function. And in this case, it looks like it gave me something that's probably a little bit closer to the actual answer for the area. Okay, so we've done left hand, we've done right hand. Okay, now we've done midpoint. There is one more, and we call this the trapezoidal approximation. I'll give you a hint. What kind of shape do you think we're going to be creating here? I don't know. Maybe some trapezoids? Maybe instead of rectangles? Ha ha ha. Everything up to this point looked at rectangles, okay? And this is going to be very similar, okay? But you're like, wait, a rectangle is not similar to a trapezoid. I mean, kind of, sort of, okay? So here's let me sketch it for you here. So again, you're going to have 0, 2/5, 4/5, 6/5, 8/5. I almost wrote 10/5. 2. That is terrible, 2. Here we go. Okay. So before we did a rectangle either going from the right-hand side, the left-hand side, or even in between. Now what we are going to do is we're going to look at the y values at every interval of delta x here, and I'm going to create a trapezoid like so. Okay, what do you notice about this trapezoidal approach here? Do you think it's more or less accurate than what we've done up to this point? That looks pretty darn close. If it looks like it's exact, it's not. It's just because I can't draw perfectly straight lines here with my tool here. But that, that's okay. So now we need to figure out, well, how do you find the area of a trapezoid? Area of a trapezoid is always 1/2 base 1 plus base 2 times your height. Okay, so looking specifically at just this first trapezoid right here. Okay, so base 1 is going to be this height. I'm sorry, it's going to be this y coordinate. Base 2 is going to be this y coordinate, and the height, remember the height of a trapezoid is the distance between the bases, so the height is going to be that 2/5 number that we had before. Okay, so the height, so the area of this first trapezoid right here is going to be 1/2 times this height right here, which this was f of 0 was 5, f of 2/5 was 125. I'm going to go ahead and write all these out so I have them. Nope, 109. F of 8/5. Okay, here we go. So now I'm going to have the area is equal to 5 plus 121/25 times the height, which is 2/5. So that's the area of the first rectangle. The next rectangle, I will repeat the process. So now I'm going to look for this trapezoid. Did I say rectangle? I meant trapezoid. So I've already taken care of this one. Okay, now let's look at the next one. So base 1, 121/25. Base 2, 109/25, 2/5. Everybody kind of see the pattern that we're going for here? 1/2. And so then I'm going to have 109. So that took care of this one. Now we're on the next one. Plus 89/25, 2/5. So that was that one. I think I can fit this all right here. Let's see. We're going to have oops, I forgot the 1/2. 1/2, 89 over 25 plus 61 over 25, 2/5 plus, that took care of that one. The last one is going to be 1/2 times 61 over 25 plus 1, 2/5. Oh, it all fit perfectly. Sweet. All right, so all of that added together. Oh, that's so gross. I wish we could clean that up in some way. Wait, maybe we could. So the area is equal to, the 1/2 is always there, right? The 2/5 is always there. Put that out front, okay? And then you've got your function values here, right? So, oh, this was f of x0 plus f of x1 plus, that was f of x1, f of x2, f of x2. I don't usually go through this whole process. Did I do the 3 twice? I did not. But I want to make sure you guys get the idea here. x3. Okay. Oh gosh, so much stuff. Well, all in all, this equates to approximately 7.28. Probably a little bit more accurate than what we had before, but it's still technically an under approximation because these trapezoids all fall entirely underneath the curve, okay, not right on the curve. So in general, here's your formula for the trapezoidal method. I equals 1 to n, the number of boxes that you want, okay? Before we evaluated our function at the midpoint, okay, now we are evaluating it at each side and essentially finding the averages of that. So it's going to be f of xi plus f of xi minus 1 all over 2, base 1 plus base 2 over 2 times your height, which is delta x. Specifically for this function, we had I equals 1 to n of 5 minus x I squared plus 5 minus xi minus 1 squared. All over 2 times 2/5. Okay. So, oh, and I forgot. We took care of that one. I just had to fill it in. All right. This was a lot, guys. Not gonna lie to you. That was kind of intense. Let's wrap all this up together, put them all together. The first one we did was the right hand. That is the summation. I equals 1 to n of just your function times delta x. That's really not that difficult. Left hand. That is the summation equals 1 to n of xi minus 1 delta x. Okay, this is implying you're on the right side. This is implying you're on the left side. Okay, we had midpoint. Essentially, you are finding the averages of your x values and then plugging those in. So f of xi plus xi minus 1 over 2 delta x. Okay, as opposed to the trapezoid approach, trapezoidal, you are finding the average of your y values. So you're saying f of xi plus f of xi minus 1 all over 2 delta x. Okay, I want you to notice that. Averaging your x values. Averaging your y values. Let me say that one more time. Averaging the x values. plugging it in, averaging your y values after you've evaluated already, okay? All combined, this gives you the 4 different methods for approximating area, okay? So I have gone through that whole process. If you have questions, concerns, complaints, well, I can't really hear any of those, but you can complain to each other all you want to. But if you have questions and you're not sure how to do this, again, Prof. Rob Bob, CalcView, CalcChat, and Khan Academy. Your homework for this is in this slideshow that I'm going to put on Canvas. So it's going to be the next 2 slides will be your homework. Use each other as a resource on this one, guys. Make sure that you guys help each other out. Some of you are going to understand this a little bit better than others. If you understand this, help sister, help brother out. Make sure they understand what's going on. And then always, always go back to all the resources that I've given you in the past.